So you've often spoken about the excitement of real-world applications. Maybe you could expand on that a little bit.
I love getting mathematical results. You know, one of the results I liked was the result about the ill conditioning of the Hessian of an interior point method. Okay, so that was good. That was a theoretical result. But what I like the best is when I can do theory and write software and have it solve a real-world problem. That's the best, having all those things. So when I worked at Bell Labs, one of the projects I work on was about indoor wireless. So we were trying to place base stations in a building to get optimal coverage of a wireless system. So we worked as a team. We had a guy that did computational geometry. We had Brian Kernahan, who did user interfaces. David Gay and I worked on the optimization. We had wireless engineers. A great experience because we all liked each other. No one was trying to take over, and we each had different expertise. So when I was working on that problem, which was very important to the company, I became interested in optimizing without derivatives. And I had not been interested in that before, and I learned what was going on, and I thought, you know, there's some room here for some work that would be interesting on these methods. So we did some software which became used by the company, so engineers would use it to design wireless systems. I got interested in the Nelder-Mead method for unconstrained optimization, which I'm still interested in, which is a puzzle and a mystery because it works well a lot of the time, but you can show it can fail miserably. So why is that? What's going on? There's no mathematical explanation for that yet. And it's very exciting when you go into a building and there's a wireless system to think, I helped optimize this. Okay, so to me, that's the best. When I was at Stanford, we worked with some people from SLAC, the linear accelerator, who wanted to improve the time that it took to turn the accelerator back on. So they had a system where it was off half the year and on half the year. And when they turned it back on, it was never calibrated correctly. Things had always gotten confused during the months of it being off. And they wanted to get it started again. And they had to adjust all these magnets. And they came to us and they said, this person at SLAC that I met, and they said, we'd like to automate this. So we took the code np-sol that you've mentioned and made a version called np-slack, which solved their problem. It used a simulation of the way the particles were accelerated in the linear accelerator, and it tried to optimize the settings of the magnets automatically using an SQP method. And it worked brilliantly. So they were very happy. The SLAC people were particularly happy because it showed that you could do some simulation rather than having to rely on turning it off, turning it on, turning it off, turning it on. And so when I drive by SLAC, I'm always thrilled. I mean, they're probably not using it anymore. So it depends on, you know, the application. But I think the individual mathematical excitement is more sort of a, I've solved that puzzle. I've tied this knot. I've done this and that. Getting the code to work is great because you think, yes, it's actually working. And then seeing the real world thing is just very exciting. I think people who work on medical applications may get the greatest thrill there. You know, I've saved somebody's life by doing this.
Although it's also very stressful because they don't want to make mistakes.
No, that's right. I mean, it's not like it's trivial to do this, but it's a very great excitement.